This question was sent to me earlier on. Can I give a little bit of help? Have a go at doing it. Pause the video if you can do it and you know this stuff well, move on. Right, if you need a little bit of help with it, let me talk you through some stuff on ionisation energy. We'll talk about general trend of ionisation energy across a period, not looking at down a group today, but we'll look at the discontinuities in that trend as well. So the general trend of ionisation energy across a period is sort of roughly like this diagram here. So as you go across a period and you increase the atomic number, the general trend is one of increasing ionisation energy. And that's because as you go across a group, as you go across a period, you increase the number of protons. So for example, if you go from lithium through to neon, and I've picked the second period of the periodic table, go from lithium to fluorine or lithium to neon, whatever. As you go across that period, you increase the number of protons, you increase the positive charge, and so you're going to increase the attraction to the outermost electron. You, whenever doing a periodicity sort of question, talk about not only the number of protons but also the number of shells, and they've both got two shells filled, and so the shielding more or less is the same between those two elements. So for lithium, you're removing that electron when you ionize it, and so there's the inner shell of 2 electrons is shielding that electron from the nucleus, and it's the same amount of shielding with fluorine if you imagine the kind of GCSE model of electronic configuration. So you'd say number of protons increase, amount of shielding is approximately the same because you've got the same number of shells. You might also add that fluorine is slightly smaller. Remember, atomic radius decreases as you go across a period as well, and so if fluorine is slightly smaller than lithium, then it follows that you're removing an electron that's slightly closer to the nucleus as well. All right, so consider number of shells and number of protons primarily. But it isn't a straightforward trend. In fact, it's more like this. So this graph from the textbook shows you that the ionisation energies increase generally across a period. So first period, second period, third period, and so on. But there are these drops along the way as well. We need to be able to explain those. But there's a couple of points I want to raise along the way. So the first time this comes up in the course is this idea that ionisation energy trends, whether it's first ionisation energy or the successive ionisation energies, which is a sort of different idea, give evidence for the existence of these energy levels. So what I mean by that is that as you go from lithium up to neon, that second shell, second energy level, if you like, is filled. And then when you get to the next one, sodium, much less energy is required to remove the outer electron from sodium. Just to remind you at this point, the definition of ionisation energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. And so the units are going to be kilojoules per mole. If you have to write an equation for it, always don't forget the state symbols too. Anyway, what we're going to, I'll go back to my bit of paper in a second, but we're looking out for the explanation for why we get to beryllium and then it drops down to boron, and then we get up to nitrogen, it drops down to oxygen, and the same thing happens in the third period. You go from magnesium to aluminium, there's a drop, and from phosphorus to sulfur, there's a drop. Right, to explain this trend, we've got to think, work out what the electronic configurations are of them fully. So what I'm going to do, I'm going to compare beryllium with boron, and then going to compare nitrogen with oxygen. So the explanation for why boron requires less energy is a bit easier, I think, than the oxygen versus nitrogen one to remember, because you're removing an electron from a higher energy subshell. Right. Remember, ionisation energy, the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. And if you think of it, I'm not going to draw proper energy levels, I'm just going to draw them like that. Remember that if that's infinity, and this is, say, n equal 1, n equal 2, if you like, the ionisation energy is the energy required to remove that electron or move that electron from here up to there. And so the higher energy the orbital or subshell, the less energy required to remove it from there. So if it was from n equals 3, less energy required to push that electron up to infinity to ionize it. Right, so that's that one explained. And then as you go from nitrogen to oxygen, the best way really to work it through is you've got 2p. This is the 2p subshell. First of all, you've got to make sure you know how to draw electrons in boxes diagrams. Make sure that the nitrogens you have, you fill the 3 orbitals separately to start with. Remember, an orbital can hold 2 electrons, but they fill one at a time first. And then for oxygen, they're each singly occupied, so the next one goes in there. So this electron is ever so slightly easier to remove than this electron or any of these electrons, because it's in an orbital with another electron, and because electrons are both negatively charged, there's a slight repulsion between them, which makes that electron ever so slightly easier to remove than this one. So that's what the trend, that drop in ionization energy, is there for. So to go back to the question that I was originally sent, you've got 3 going up like so, and then a drop. And the only place that happens is here, 3 going up together and then a drop. And it's not the drop that you get down to sodium, which is a huge drop. It's only a little drop. I mean, I think that should be there, but I'm not going to argue with you. Example, you can't see it. I think the drop should be slightly higher than that, but there we are. It's a drop, 3 in a row and then drop. That's 3 in a row, boom, 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 and then a drop. So this is group 13, 14, 15, and so the answer had to be B. That was the group 14 one. And that was the answer. Hope that's useful. Do learn your periodicity. It's really easy, really common, stuff you can just get your head around and learn, and guaranteed to get a few marks. Any more problems, let me know.